So today we're going to see a simple mathematical analysis on simple harmonic motion. Our objective? To prove that the time period of a pendulum is directly proportional to the string length. We're going to use some assumptions just to keep our math simple. Using the law of conservation of energy, which states that potential energy plus kinetic energy is constant at any point in the swing, we can see that the potential energy is maximum at extreme positions while the kinetic energy is zero, and in the mean position, kinetic energy is maximum while potential energy is zero. Using this, we can derive our maximum velocity at equilibrium to be root of 2gh. This is simple harmonic motion, so the velocity of the pendulum can be represented as a sine function. Here we have only taken the absolute value of the velocity. So our average velocity amounts to 0.637 times our maximum velocity, which yields this expression. So our time period is our distance per cycle divided by our average velocity. Our distance per cycle is twice the arc length, which is 4L theta p meters. Inputting this into our time period equation, we get this function, which boils down to 2 pi root of L by g seconds per cycle for a given theta p. We can see that time period is directly proportional to length and inversely proportional to velocity. Velocity is directly proportional to the square root of length, and this boils down to the time period being directly proportional to the square root of length. Since the square root function is always increasing, an increase in length will correspond to an increase in time period. So to summarize, a simple pendulum's time period is directly proportional to the string length, and our derived formula yields values that are very close to the established formula of 2 pi root of L by g. I also conducted an experiment with various string lengths, and all three values, empirical, derived, and established time periods, tally up. Thank you for listening.